Walter Hostetler's electric bill last August was $11.42. His neighbor across the street, same floor plan, same square footage, same Lancaster County heat, paid $286 that month. Walter is 73 years old. He is a retired electrician. He does not have solar panels. He does not have a geothermal pump. He does not have a Tesla battery wall or a net metering contract with the utility. What he has is a wooden privacy fence. And bolted to the top rail of that fence, spaced about 8 feet apart, are 4 slender vertical cylinders. Each one is roughly the diameter of a coffee can. Each one cost him about $22 to build. They spin almost silently in the afternoon breeze. They have been spinning, in one version or another, since 2009. That fence line right now is generating electricity. And the reason most people watching this video have never heard of it, the reason you will not find a segment about it on any home improvement channel, any morning news show, any home and garden network special, is not because it doesn't work. It's because it works too well at too small a scale. And small scale is the one scale that utilities cannot survive. Stay with me on this. Because by the time we finish today, you are going to look at your backyard fence completely differently. You are going to understand something that the USDA literally printed in a public bulletin in 1935, distributed for free to any American farmer who asked for it, and then quietly stopped printing in 1946 when the grid reached the countryside and made that knowledge commercially inconvenient. Let's start with Walter's fence, because the image matters. It is a standard 6-foot wooden privacy fence. The kind you see in every suburban backyard from Ohio to Oregon. The kind covered in Section 4, Paragraph 9 of the Whispering Pines Estates Homeowners Association Covenant. That section prohibits, quote, any structure exceeding 12 feet in height intended for the generation of electrical power. Walter's turbines are 5 feet tall, mounted on a 6-foot fence. Total height, 11 feet. He read the bylaw twice before he ever picked up a wrench. The HOA attorney sent a cease and desist letter dated August 11, 2020. Walter sent back a single photograph and a copy of the bylaw with the relevant clause highlighted in yellow. The fine was rescinded within 9 days. No court, no lawyer, just a man who read his own paperwork. But let's back up to how this started. Because the fence is the result, not the beginning. The beginning is a question that every homeowner who has ever opened a July electricity bill has asked, usually while standing in front of an open refrigerator at 11 o'clock at night. Where is all this money going? If you live in a region with real summers, Pennsylvania, Texas, the Gulf Coast, the Midwest, the Southwest, you know what a cooling load feels like. You know the moment in June when the thermostat stops being a setting and becomes a negotiation. 78 feels too warm. 74 feels expensive. You find yourself closing blinds you never used to close, setting ceiling fans to spin in directions you had to look up, waking up at 3 in the morning because the air conditioning cycled off and the bedroom went from tolerable to oppressive in 40 minutes. Walter Hostetler spent 31 years as a commercial electrician. He wired schools, office buildings, a hospital wing outside reading. He understood exactly where his money was going and exactly why his utility had no interest in helping him reduce the amount of it. Utilities in the United States are regulated monopolies. They are entitled by law, in most states, to a guaranteed rate of return on their capital investments. The more infrastructure they build, the more wire, the more transformers, the more substation equipment, the more they are legally permitted to charge. Conservation is not in their financial interest. Efficiency is not in their financial interest. A customer who cuts their consumption by 30% is, from a business model perspective, a problem. Walter understood this. He had spent a career installing the infrastructure that made it possible. And when he retired in 2007 with a pension and a house that was paid off, he started thinking about the wind. Specifically, he started thinking about the wind that blew across the open half-acre behind his house every single afternoon, and how completely everyone around him ignored it. He had seen wind turbines. He had driven past the big horizontal ones on a road trip through the Allegheny Plateau years before. He knew they were not relevant to a backyard. The minimum tower height for a horizontal turbine to reach clean laminar airflow above ground turbulence is about 30 feet. Zoning in his development max structures at 12. The math was closed before it started. But Walter had also spent 31 years looking at problems sideways. And sometime in the spring of 2008, he came across a reference to vertical axis wind turbines in a back issue of Home Power magazine he found at a library sale. The article mentioned a design called a Savonius rotor. It mentioned a junkyard alternator. It mentioned PVC pipe. He set the magazine down and started writing a parts list on the back of an envelope. Now, before we get into what Walter built and how you can build it, I want to spend a few minutes on why this technology is not more widely known. Because the answer is not complicated. It is, in fact, embarrassingly simple once you understand the economics. The American Wind Energy Association, the main trade group for the wind power industry in the United States, is funded primarily by manufacturers of utility-scale wind turbines. Companies like GE, Vestas, Siemens. These machines are enormous. A single modern utility turbine is 200 meters tall, costs $3 to $5 million, and feeds a grid that then sells the power back to you at retail. The AWEA has spent the better part of 2 decades reinforcing the narrative that wind power means those towers. That it means open prairies and offshore installations and federal leases and transmission infrastructure. That residential wind is a niche curiosity. That vertical axis designs are inefficient and unproven. That last claim is the one that engineers who study the data find particularly galling. In 2011, a research team at Caltech led by Dr. John Darrieus, now a professor at Stanford, published a peer-reviewed study in the Journal of Renewable and Sustainable Energy demonstrating something that should have been front-page news in every home improvement magazine in America. An array of vertical axis turbines, spaced closely together in a coordinated layout, produced up to 10 times more power per square meter of land than equivalent horizontal turbines. 10 times. In a field study. With off-the-shelf hardware. Published in a peer-reviewed journal. It was not front-page news. It was not covered by the trade press. It was cited in a handful of academic papers, and then, for all practical purposes, ignored by everyone with a financial interest in the existing conversation about wind energy. Why? The answer is embedded in the finding itself. Vertical axis turbines scaled down. You can build one for $90 in an afternoon. You can mount it on a fence you already own. You do not need a tower assessment. You do not need a zoning variance. You do not need a certified installer. You do not need a utility interconnection agreement. Horizontal turbines do not scale down this way. Below a certain rotor diameter, their efficiency drops sharply. They need tall towers to reach clean air. They need to yaw, to physically rotate to face the wind, which requires mechanical complexity and maintenance. They are, below about 5 kilowatts of rated output, a poor economic proposition for a homeowner. Vertical turbines, particularly the hybrid Savonius Darrieus designs we're going to talk about in detail, are the opposite. They get more interesting, more practical, and more economically viable the smaller and simpler you make them. That asymmetry, vertical good at small scale, horizontal good at large scale, explains everything about why you know one and not the other. But here is what I find most interesting about the story, and the part that never makes it into discussions about energy technology. The people who never forgot were the Amish. Not because of ideology. Not because of a rejection of technology as such. That is a simplification that does not hold up if you spend time in Holmes County, Ohio. The old order communities use technology constantly. They just use it on their own terms, with their own criteria. And one of those criteria is that a piece of equipment should be reparable by the person who uses it, with parts they can source locally, without depending on a corporation or a grid. In Holmes County, there is a farm owned by the Yoder family. On that farm, there is a homemade vertical rotor built from sheet metal and bicycle parts that has been pumping water and charging a 12-volt battery bank since 1978. 47 years of continuous operation. The bearings have been replaced twice. The blades never. The eldest son, Amish, when asked why they chose vertical rather than the more common windmill designs you see on Plains farms, said something that is the entire engineering case for this technology in one sentence. He said, "The wind doesn't come from one direction here. It comes from all of them. So we built something that doesn't care." That is, in plain language, the fundamental physics advantage of a vertical axis design over a horizontal one at residential scale. A horizontal turbine, the kind on a tower, the kind in wind farms, the kind marketed for residential use, needs to face into the wind. It spins because the wind pushes the blades from one direction. When the wind shifts, the turbine has to yaw, to rotate its entire assembly to track the new direction. At utility scale, this is accomplished with electronic sensors and servo motors. At residential scale, it means a tail vane and a bearing assembly that wears over time. More importantly, a horizontal turbine needs clean, laminar airflow, the kind that exists at altitude, at 30 feet, at 50 feet, at the elevation of a utility tower, at 6 feet off the ground, in a suburban backyard surrounded by houses and fences and trees and sheds. The air is not clean and laminar. It is chaotic. It swirls. It reverses. It gusts from 3 directions in the same minute. A horizontal turbine in that environment spends most of its time either stalled, yawing, or fighting turbulence. A vertical axis turbine does not care. It accepts wind from every direction simultaneously. It does not yaw. It has no preferred orientation. The same rotor that catches a northerly gust catches the southerly that follows 30 seconds later. Amos Yoder's observation, "We built something that doesn't care," is not folksy wisdom. It is a precise description of omnidirectional aerodynamic acceptance. And because the axis is vertical, the generator sits at the bottom, at ground level, where you can service it with a screwdriver and a flashlight without climbing anything. This is not a small point. Maintenance accessibility is a major factor in the long-term economics of any home energy system. A generator you cannot easily reach is a generator you will not maintain. A generator you do not maintain fails earlier than its designed lifespan. The Yoder family has operated their vertical system for nearly 5 decades, partly because when something needs attention, it takes 20 minutes to fix. Let's talk about the specific design that Walter used and that the Yoder family refined over 4 decades, because this is where the engineering gets genuinely interesting. It's called a Savonius Darrieus hybrid. 2 different aerodynamic principles working in combination. The Savonius component is the scoop. Imagine a coffee can cut in half lengthwise, with the 2 halves mounted on a central shaft with their openings facing opposite directions. Wind entering the open face of one half pushes it forward. The other half, presenting its curved back to the wind, offers less resistance. The difference in drag between the 2 sides creates rotation. This is called drag-based generation. A pure Savonius rotor is not dramatically efficient, roughly 15% of available wind energy converted to mechanical rotation at its best. But it has one critical quality: it self-starts. You do not need a minimum threshold speed. In almost any breeze at all, a Savonius starts turning. The Darrieus component is different. It operates on lift rather than drag, the same aerodynamic principle as an airplane wing, but oriented vertically. The curved vertical blades of a Darrieus rotor, as they travel in their circular path around the shaft, generate lift force that contributes to rotation. At higher rotational speeds, this lift-based mechanism becomes dramatically more efficient than drag-based generation. A well-designed Darrieus can reach 40% efficiency. But a pure Darrieus has a fatal practical flaw: it cannot self-start. It needs to be spinning above a threshold RPM before the lift mechanism kicks in. In a residential context, that means you need a motor to spin it up on still days, or it just sits there. The hybrid solves this. The Savonius component provides enough starting torque in light winds to get the rotor moving. Once it's moving, the Darrieus lift component takes over at speed and drives efficiency up dramatically. The result is a design that self-starts in winds as low as 4 miles per hour and reaches meaningful generation efficiency across the range of wind speeds actually present at residential fence height. 4 miles per hour. That is the speed of a slow walk. That is the speed of a flag moving gently. That is the speed of wind that does not even flatten grass, but that you can feel on the back of your hand on a still summer afternoon. According to the National Renewable Energy Laboratory's Wind Integration National Dataset, a publicly available resource with wind speed data for every zip code in the continental United States, the average annual wind speed at 6 feet of elevation in most of the country falls between 7 and 11 miles per hour. 7 to 11 miles per hour. That is what is available at fence height, on average, throughout the year in most of the United States. It is enough to run a Savonius Darrieus hybrid continuously during daylight hours on most days of the year. You are sitting in a power plant. You have always been sitting in one. You just were not told. Now, let's get into the bill of materials. Because I know that is why many of you are here. And the numbers are worth going through carefully, because this is where the cynicism usually enters the conversation. Walter posted his parts list on the Reddit forum r/offgrid in November of 2021 under the username Walthos. It looked like this. 1 6-inch diameter PVC sewer pipe, 10 feet long, cut into 2 5-foot sections, $14 at a plumbing supply house. For sheets of corrugated aluminum roofing flashing, $11. 1 automotive alternator from a junkyard Subaru, $15. 2 skateboard bearings, $6. 1/2-inch threaded steel rod, $4. Stainless steel hardware, $8. 1 30-amp PWM charge controller, $19. Total, $77. He rounded to 90 in his post to account for paint and silicone sealant. The whole assembly took him a Saturday afternoon and part of Sunday morning. He built 3 more in the following weeks. By his account, the 4th took under 3 hours from cutting the PVC to mounting it on the fence. Now the comments on that post are where this gets interesting. One user, a retired Boeing aerospace engineer posting from Spokane under the name Handleblade Pitch, replied that he had built a similar array in 2019 and was averaging 2.1 kilowatt hours per day across 4 turbines. Over a full year, that is roughly 760 kilowatt hours. For context, the average American household uses somewhere between 8,000 and 10,000 kilowatt hours annually. For $90 turbines generating 760 kilowatt hours is approximately 8 to 9% of total household consumption, just from fence posts. Walter, with 34 turbines along his fence line, is producing substantially more than that.